Hello. Today this is my third experiment in my UVRT dataset of RPG model. So in this video I want to experiment with IAFNO, yeah, FNO. This is FNO variation model, but for my UVRT dataset it's still the same. The special treatment is still same, random crop window. So first I want to explain about the YAFNO first, but YAFNO is the enhanced version of the AFNO, which is the AFNO is the variation model of FNO, and AFNO stands for Adaptive Fourier Neural Operator. So what is the innovation from this FNO model? Actually, it's only one. It's just a diagonal block. From that innovation, we can bring 3 points of innovation in here. So first, we don't need to do a hard thresholding in AFNO. And in FNO, usually we will do after we do the FFT, we will do hard thresholding. For example, if our input image is 1000 times 1000 for the height and width, after we process the FFT, the shape in the frequency spectrum will be 1000 times 500. The last dimension will be halved like that. And if we process all of them, if we didn't do the hard thresholding, then in the matrix multiplication, in this step in here, the total memory or computational cost that we need to do to process all of them will be very big, or yeah, it will be very big computation. And then in AFNO we don't need to worry about that because the diagonal block. So basically diagonal block in here is like this. And wait, I need to explain about the weight sharing first, I think. So it's related to diagonal block. So in FNO, I will explain it in this scribble, I think. So in FNO, our input shape is like this. The first dimension is batch, and then I, X, Y. X and Y in here, this is the output of FFT. Like I said before, that if our input is 1000 times 1000, then the X and Y in here, maybe X will be 1000 and Y will be 500, or in the reverse. And then this is the shape. And in the after we do the FFT, usually we will multiply it by some weight in the model. So the shape of the weight that we will multiply with the FNO input is like this. For your information, I in here, this is the embedded dimension that we state, or we could say it as a context width in here. So this is the embedded dimension. And then OXY. So here, this is the input embedded dimension, and O in here, this is the output, the dimension that we want for our output. X and Y in here, must be the same with the X and Y of the input. And if we multiplied it, then it will be the dimension that will be involved in the matrix multiplication will be I, X, and Y. And for the way, of course, all of them. And then if we multiply it, this multiplication will be repeated B type. But in AFNO in here, our shape will be, look, in AFNO step here, before we input the input to the multiplication, we will reshape the data. So that's why we have the shape of the data is quite different with the FNO. In here we have B, X, Y, N, and B. And for your information, the embedded dimension in here, N and B, is from the embedded dimension, and this is Why it's called the diagonal block? Because we will divide the total embedded dimension to n and b. N in here is the total number of the block, and block in here the size of the block. And for the shape of the matrix, as for the shape of the weights that we will use in AFNO, is the shape is like this. So it's n times b, and then because the shape is like this, then the dimension that will be involved in the multiplication is just in the input of the AFNO. It's just n and b. So it's like if we compare it with FNO, the dimension that will be involved with is just e. In here it's just n and b, which is the e, which is the I in here, right? So that's why I said in here, yeah, because the shape of the weight is like this. If we do the matrix multiplication, because it can, you see in here, it can cover all of the dimension in the AFNO input, right? So that's why it can cover them. Then this dimension will be shared for every point in x and y and bets. So that's why in AFNO they said that they do a weight sharing. How they do it? It's like this. So this is the math of that weight sharing. And yeah, it's quite similar with the if you remember about multi-head attention. Yeah, in multi-head attention they do something like this. So the embedded dimension, they will divide it with some number that can be dividable of the total embedded dimension, and then because of that, the total computation in the attention network will be significantly reduced. And also in the case of the attention network, because the head of the in the model in the attention network is increasing, then like the real head in the real life, then this head can take attention for other things or many things in the data in the input. Okay, that's for AFNO. Yeah, basically their main innovation is this weight sharing and diagonal block. Yeah, and diagonal block is related to that weight sharing, I think. And for the final activation function, they use the shrinkage function. So it's because they argue that in real world image that we really care is sparse in nature. Thus we can apply the FFT. So all the important feature in the image naturally will place it in lower frequencies. And in the other hand, in the high frequency, it will be consist of some noise or unimportant feature. And if that feature that is really unimportant, then naturally when we multiply it by some dense layer or etc., they will naturally they will have a minuscule value. So that's why this function, the function the function of this function is just to reduce all those unimportant features from the really small value or minuscule value to exactly zero. The function is like this. And overall, the algorithm of the AFNO is like this. So first we do the FFT and then reshape, and then we we do a matrix multiplication in block MLP in here, and then reshape again, and then do softering, and then inverse the FFT, and then plus bias like this. So yeah, it's not that hard. And for IAFNO now, so IAFNO is the innovation or the enhanced version of the AFNO. And in IAFNO, basically in IAFNO, they bring back the patch embed layer. So in AFNO, they say that how the model work is like visual transformer, but actually they don't really use a patch embed layer like this. In IAFNO, they literally using the batch embed layer like in visual transformer. And then in here, the main innovation in IAFNO is it's called yeah, it's called implicit method. So basically, the input the input for the IAFNO will be processed many times by the same layer or by the same block computation. And they say that how this works is something similar like implicit method in numerical model. So implicit method in numerical model is the way to solve the PDE other than explicit method where we using a central difference or forward difference. In the IAFNO, they want to replicate how the implicit method works. So they will process like this input many times using a certain block. Actually, you can choose if you want to make a 2 block or 3 block or just 1 block. For example, if we using a 3 block and then we want to loop it like 2 times, then 2 times 3 6, there will be 6 time processing for the input. But the one of the things that I take note in the IAFNO paper is this. So you know that I said before that IAFNO is the enhanced version of the AFNO, right? And in the diagonal block in the AFNO, to reduce the computation, we divide the embedded dimension to some number that can be dividable by the number of the embedded dimension, right? For example, if the embedded dimension is 100, then we can choose, for example, 5 or 25 or 2 or 10, something like that. And that's why the computation in the AFNO is reduced, right? But in IAFNO, in the original paper, they said that the best performance model is using the number of blocks as 1. And that's why I said that if the number of blocks is 1, then there's no really diagonal block. The full advantage of the diagonal block is really not used. There's no cheaper computational cost. So that's why this is one of the things that I want to test in my experiment in here. So there's 2 things that I want to test in my experiment. First is the the implicit method that they claim in IAFNO paper is really works. So that's why in here to test them, I for the n layer, for the implicit loop or n layer in the script, here in the script the variable is n layer. And for your information, in the paper of IAFNO, they present their original code in the GitHub page, and I just use that. And originally, they use this IAFNO model to process a 3D turbulence prediction. But in my case, I want to process them to process a 2D turbulence prediction. So yeah, I just need to modify it a bit, and then here I will test the n layer using 1, 10, and 20. And for my second experiment, I also want to test if num blocks must be really just 1, or maybe we can make, for example, we can make num blocks to be 8 or 4, because in the original paper they're using the embedded dimension. The embedded dimension they are using is 200, and that's why I want to test if 8 or 4 or 10 can really works in the IAFNO model for my case. And yeah, I already done the experiment, so now I will explain the result. So here, this is the result for the n layer 1, 10, and 20. And since I am using the UVRT or UVLH and temperature parameter for in the RPG model. Here we have 4 output like this. 2, 3, 4, yeah, 4 output. And as you can see here, consistently for all the case, the n layer 1 is the error is really significantly higher than the n layer 20 and 10. So that's why in here we can eliminate the n layer 1. And I think from this result, I think the implicit part of the or the implicit machine that they design in IAFNO is really work. So, and if we zoom in between the n layer 10 and 20, as you can see here, the result is not that different, but I think n layer 20 is much better, and no, it's a bit better than n layer 10. So yeah, the winner is n layer 20. And I think if we increase the n layer to 30 or 40, I think there will be no much difference with n layer 20. Now for the result of the second experiment, here first I want to show you the prediction in Indonesia region and senior cyclone. And as you can see here in the n layer 20 using num block 1 as the original paper. As you can see here, for the IAFNO, they can replicate the cyclonic pattern in the Indian Ocean with the good accuracy, I think. Yeah, in FNO, I think there is no movement at all, but IAFNO successfully captured the pattern of the cyclonic pattern with good accuracy. But in the senior cyclone case, as you can see here, the cyclonic things must be moved from here to the lower region in here. But in the IAFNO with numblocks 1, they predict that this cyclone will be extinct. So, as you can see, as time goes on, the cyclone is gone. And for here, for the numblock 8, it also can replicate or it can predict the cyclone movement or cyclonic pattern movement here. And for the senior cyclone case, I think it's the same with the IAFNO with now numblock 1. The IAFNO in here also predict the extinction of the cyclone. And here is the graph of the performance for the Indonesia region. And as you can see here, numblock 8 from 4 case. Here, the first case, second case, third case, and fourth case. From the 4 case, numblock 8 outperformed numblock 1 in 3 of 4 cases. And here, this is for the cyclone prediction, and looks like numblock 1 outperformed numblock 8. Yeah, so the first case, the winner is numblock 8, and the second case is numblock 1. So yeah, I think we need to really test the performance of the number of the block. We really need to increase the test case. So that's why in my experiment here, my conclusion is the implicit method machine that they designed in IAFNO is really works. And the second conclusion is I think we don't need to really choose the numblocks 1 as the settings in IAFNO. We can choose numblock 8 for the setting for the model. Okay, see ya. See you in the next experiment.